In the previous lessons, we've talked about the basics of exponential and logarithmic functions. In this lesson, I'd like to show you a few ways that these kinds of functions can be used to solve problems. I'd like to start out gently with some basic equation solving. But before we do that, let me mention one very important rule called the change of base formula, which helps us with logarithmic functions. So here is the change of base formula. Take a number m, which is a positive number, and b, which is positive as well as c, where b and c are not allowed to be equal to 1. Then you can change the base of log base b of m in the following way. Log base b of m equals log base c of m divided by log base c of b. So, for example, this formula tells me this, that the log base 2 of 100 is equal to log base 10 of 100 divided by log base 10 of 2. It also tells me that the same log base 2 of 100 can be rewritten as log base 7 of 100 divided by log base 7 of 2. And whatever other base you want to choose for that right-hand side, you may choose, as long as it's a legal base to choose. So this formula comes in really handy if you're trying to use a calculator to approximate answers, but you only have something like a common logarithm key, which would be log base 10, on your calculator. And many calculators only have really two buttons that work well for logs. It's the log base 10, often just the LOG button, and the natural logarithm, which we really haven't talked about yet, which is the LN button. So this change of base formula can be really helpful if you need to use a calculator to do any sorts of approximations. Now, with that said, I'd like to move to an example where we try to approximate the solution of a specific equation. And in this case, it's going to start out exponential, but you'll see how the logarithms sneak in before the end of this. So here's the example. Start with the equation 6 raised to the 5x equals 40 and approximate a solution for x. Well, a general way to attack these kinds of problems is to actually take the logarithm of both sides of the equation. Now, why is that true? Well, you're trying to isolate the variable, in this case the x, in order to solve for it. When you take a logarithm, it's going to help you do that. And in this case, you're going to want to choose the log base 6 because the original equation has 6 being raised to a power. Now, here's how this works. Start with your 6 to the 5x equals 40 and just take the logarithm of both sides. So you'll have log base 6 of 6 to the 5x equals log base 6 of 40. Now, remember, one of the properties we've seen of logarithms is that exponents that are hiding inside the logarithms can be pulled out to the front. So the log base 6 of 6 to the 5x is the same as 5x times log base 6 of 6. So now I have 5x times the log base 6 of 6 equals log base 6 of 40. But the log base 6 of 6 is the number that I would raise 6 to get 6. That means that the log base 6 of 6 is just 1. So the left-hand side is now just 5x times 1, or 5x, and that equals log base 6 of 40. Do you see how choosing the log base 6 here has now helped us tremendously to getting x by itself? If I now just divide both sides by 5, I'll have that x equals log base 6 of 40 divided by 5. Now, I don't have a log base 6 button on my calculator. I mean, you'd have to have a really big calculator, if you think about it, to have a bunch of different log buttons. But I do have just an LOG button, which stands for log base 10. So let's take our answer and rewrite it in terms of log base 10, and then we can use our calculator. So what I'll have when I do that rewriting is x equals log base 10 of 40, or just log of 40, divided by log of 6, and then that's all divided by 5. And that's the same as log of 40 divided by 5 times log of 6. And that's the kind of answer that I want if I want to punch this into a calculator now. And when I do that, if I just want an approximation, I'm going to find that x is approximately equal to 0.41176. Now, we should check our answer, at least try to see if it's in the right ballpark, if you will. So you can pick up your calculator once again and type in the following: 6 raised to the 5 times 0.41176, and see what it gives you. And in that case, you're going to have something like 6 raised to about 2.0588, and that is approximately equal to 39.99979 or something along these lines. Notice that that's extremely close to 40, and that's a good signal because our original equation said we wanted 6 to the 5x to equal 40. So this is an indication that we have a very good approximation, and so we're done. Now, before I move to the next example, let me just make a quick comment. I chose, in the example we just completed, to take the log base 6 and work through the problem in that way. I could have done the log base 3 of both sides, for example, instead of the log base 6. That would have been legal mathematically, but it would not have helped me very much. By choosing log base 6, I was able to get rid of that base of the 6 in the 6 to the 5x, and it took care of things very nicely. Now, let's move to another example. I want us to solve 3 to the 2x plus 1 equals 144. So let me suggest that you try this one on your own and see what you get for x, and then we'll come back together. Now we're solving 3 to the 2x plus 1 equals 144. If you think about the previous example, the way I want to do this as a starting point anyway is to get that 2x plus 1 away from that 3 by taking the log base 3 of both sides. So I'm going to then have log base 3 of 3 to the 2x plus 1 equals log base 3 of 144. Now, the left-hand side becomes 2x plus 1 times log base 3 of 3. That's again using the property of logarithms that allows exponents to come down in front. And the right-hand side is still just log base 3 of 144. The log base 3 of 3 is 1 because 3 to the 1 equals 3. So the left-hand side simplifies to 2x plus 1, and that's now equal to log base 3 of 144. Now you just need to get x by itself, and I realize the right-hand side's a little messy, but just think of it as a number for now. We're just trying to get that x by itself. So subtract 1 from both sides, and you'll have 2x equals log base 3 of 144 minus 1, and then divide by 2, and you'll have x equals log base 3 of 144 minus 1, all divided by 2. Now again, if you're trying to approximate this and actually get a number here for x, at least to a certain number of decimal digits, you're going to need to convert it away from log base 3 into some other logarithm that your calculator allows. And again, most calculators will allow you to do log base 10, which is known as a common logarithm, and that button is often just denoted as log, but it's really log base 10. So I can rewrite this answer for x then using my change of base formula in the following way. Instead of having log base 3 of 144, I would convert that to log of 144 divided by log of 3. And so x is really also equal to log of 144 divided by log of 3 minus 1 all divided by 2. And now if you are careful about how to calculate that on a calculator, and you do have to be careful about what you do as you do those calculations, you'll find that x is approximately equal to 1.76186. Again, we should check that this is in the right ballpark, that it's about the right size, about the right amount. So the way you do that is to take the answer we just found, 1.76186, which is just an approximation, and plug it back into the original equation. This is how we've been checking solutions all course long. And in that case, we're going to do 3 raised to the 2 times 1.76186 plus 1. And that's going to be 3 raised to the 4.52372. Now, if you ask a calculator to tell you what that is, it's going to give you an answer something like 144.0002 or something like this. Well, we wanted 144, so we know we're in the right ballpark. There's a little bit of error, but that's because of the approximation that we did. We know that our final answer is approximately 1.76186. Now, let's transition quickly to solving some equations that start out with logarithms in them, rather than starting out with exponential functions in them. So why don't you try this one first on your own, and then we'll come together to see how you did. Approximate the solution of 3 times log of x equals 7. Okay, you have two choices here, in my opinion. One is to simply divide both sides by 3, which is what I would suggest, or you could rewrite the left-hand side as log of x cubed using the law of logarithms, or the properties that we've been talking about with logarithms. I personally think that that's a bit of overkill. I would suggest we just start by dividing both sides by 3. And when I do that, I'll go from 3 log of x equals 7 to log of x equals 7/3, or 7 divided by 3. Now, you want to get x by itself. That's the key here. How do you do that? Well, you basically do the same kind of thing that we've done in the other examples, except now you already have a log in the problem. So what you want to do is raise both sides to the 10, basically. In other words, instead of having log of x equals 7/3, I want to do 10 raised to the log of x equals 10 to the 7/3. Now, why did I choose 10? Well, remember, log of x means log base 10 of x. Anytime you see a log and it doesn't have subscript, it means that there's an understood subscript of 10 there. So that's why I took 10 on both sides and raised 10 to the log of x on the left, and I have 10 to the 7/3 on the right. Now, what is 10 to the log of x? Well, it just turns out to equal x, because that log of x is equal to the log base 10 of x. So believe it or not, by doing what we just did, we've just gotten the left-hand side to become x. And the reason, by the way, that that happens is because that the exponential function 10 to the x is the inverse function of log base 10 of x, or just log of x. And so what I've done there is put the two functions together that undo one another as inverses. And in the process, then, the left-hand side just becomes x. So my answer is x equals 10 to the 7/3. Now, I don't know what 10 to the 7/3 is exactly. If you ask me what 10 to the 2nd is, or 10 to the 3rd is, I think I could do that. 10 to the 2 is 100, and 10 to the 3 is 1,000. But 10 to the 7/3, I really don't know. So I can pull out a calculator and ask, what is that? And when I do, I'll find that x is about 215.443. Now, we could check our work again by plugging this amount back into the original equation and checking to make sure we're okay. So let's do that. If I plug in 215.443 into the log function, the left-hand side of the original equation will become 3 times log of 215.443, which is about 3 times 2.33333 or so, which is 6.99999. That's extremely close to 7, and again, that gives me a hint that I've got the right answer. Now let's solve one more equation that involves some logs, and this one's a little bit different. So I'm going to let you try it first, and then we'll come together and check our work. Solve 2 times log of x plus log of 4 equals 2. Now there are a lot of ways you might start attacking this problem, but bottom line, you need to do whatever you can to get the left-hand side written as one logarithm. Remember, I tried to show you a few examples in a previous lesson about how you would start with 2 logarithms the way we have here and combine them into one using these properties of logs. So let's do that here. Let's get the left-hand side to look like log of one thing. So I started with 2 log of x plus log of 4, and that's the same as log of x squared plus log of 4. Remember, there's a property that allows me to move these exponents down in front or put them back up if I want. And now the log of two things added together can be glued together as log of one thing. And I do that by multiplication, so that what I really have on the left-hand side is log of 4 times x squared. So log of x squared plus log of 4 is the same as log of 4 times x squared. So my equation has now become log of 4x squared equals 2. Notice the right-hand side hasn't been touched at all. Now, how do I solve this? Well, now I go back to the same idea from the previous example. I now do 10 raised to the log of 4x squared equals 10 to the 2. And the 10 raised to the log of 4x squared just becomes 4x squared. And the right-hand side now is 10 to the 2, which is equal to 100. So I have 4x squared equals 100, x squared equals 25 then, so x equals plus or minus 5. Now, I definitely need to check these answers because I might have what we called in an earlier lesson extraneous solutions. In other words, numbers that sneak in and act like they're solutions when they really aren't. So let's plug these in. When I plug in x equals 5, I'm going to have 2 times log of 5 plus log of 4 equals 2. I'm plugging that back into the original equation. And that's the same as saying log of 5 squared plus log of 4 equals 2, or log of 25 plus log of 4 equals 2, or log of 25 times 4 equals 2, and that's saying log of 100 equals 2. Now, log of 100, remember this is common logarithm, so it's log base 10 of 100, so that is equal to the number I would raise 10 to get 100. Well, I would raise 10 to the second power to get 100. So the left-hand side is actually just a 2, so I'm saying 2 equals 2, and that's true. So x equals 5 really is a solution. Now, let's try negative 5. Well, I plug in negative 5 to the original equation, and I'm going to have 2 times log of negative 5 plus log of 4 equals 2. And at this point, we have to just scream, stop. And that's because remember that the domain of any logarithmic function is always the positive real numbers. So log of negative 5 makes absolutely no sense. I can't plug negative 5 into the logarithmic function. And therefore, because of that lack of ability to plug in the negative 5, I know that x equals negative 5 is really not a solution. And therefore, to finish the problem, I need to say that the only solution is x equals positive 5. Now, I'd like to transition to a very different kind of problem involving a certain type of logarithmic and exponential function. We already showed that common logarithms, logs base 10 for example, have some special usages. I sort of hinted to the fact, for example, that they might be useful in things like calculating pH. I mentioned that very briefly in some introductory comments earlier. And I also pointed out a lot that you need the log base 10 for a lot of calculator work because most calculators only have really a log base 10 function and another log which we're going to introduce now. So the log base 10, the common logarithms, are very important. But it turns out that there's another very special and important logarithmic function, and it's the logarithm at the base e. Now, I don't have time really, or the mathematical tools that we would need to tell you everything you might want to know about this number e, but I can guarantee you that it's an extremely important number, and it's defined using the concept of a limit that you and I would find in a first-year calculus course. So I'm not going to tell you everything about e that you may want or need to know today, but I can tell you a few things. So first of all, e is approximately 2.71828. You know, we often say that pi is approximately 3.14, and that's true. Pi is approximately 3.14. Here we have another number, e now, which is approximately 2.71828. Secondly, I can use this number e as the base for an exponential function, y equals e to the x, just like I can write down y equals 2 to the x or y equals 3 to the x. And since e is bigger than 1, it's going to be a growth factor. So the graph of y equals e to the x is going to have a very similar shape to the graph of y equals 2 to the x or y equals 3 to the x. Okay, now once I've defined y equals e to the x, I can define its corresponding logarithmic function for that base. Now we could write it as y equals log base e of x, but to be very honest with you, that gets a bit cumbersome. So the understood notation for this logarithmic function with the base e is just y equals ln of x, and we read this as y equals the natural logarithm of x. Think of the n in ln as standing for natural. Now the ln function also satisfies the same properties of logarithms like all of the other logarithmic functions satisfy. So for example, we've seen already that I can take log of 2 plus log of 3, and this equals log of 2 times 3 or log of 6. The same is true of ln. ln of 2 plus ln of 3 is equal to ln of 2 times 3 or ln of 6. Now that's just one example, but the ln function is going to behave like the other logarithmic functions when it comes to those properties. Now, probably the best known formula that's related to the functions e to the x and the natural logarithm of x is traditionally known as the PERT formula, P-E-R-T. It comes from a certain type of financial investment question, and the formula is given by A equals P times E to the RT. You can see why some people call it the PERT formula. A equals P times E to the RT, where A is the amount of money in one's account at any time t, P is the amount of principal, so it's the amount you put in initially or when the time t was equal to 0 when you started the account, R is equal to the interest rate, and T is the time in years. Now, it's important to note that this PERT formula only works if the interest on the account is compounded continuously, as opposed to, say, earning interest on a yearly basis or a monthly basis or even a daily basis. If your account is earning interest in one of these units of time, like daily or weekly or monthly, then you actually have to use a different kind of formula that involves a different kind of exponential function. But for continuously compounding interest, the PERT formula is the one to use. Now, let's look at a couple examples of using this PERT formula because it's actually very useful and it involves this exponential function e to the x. So here's the example. An initial investment of $1,000 is now valued at $1,750.67. The interest rate is known to be 8% compounded continuously, and that's the key. We know we can use the PERT formula because we know that the interest is being compounded continuously. How long has the money been invested in this account? Did you notice that the problem didn't tell us how long it had been there? It just told us how much they had at the beginning and how much they have now and what the interest rate was. So we now want to try to figure out how long the money has actually been in the account. Again, since the phrase compounded continuously arose in the problem, I immediately know that I want the PERT formula. So the PERT formula reminds me that A equals PE to the RT. Now, I've got to figure out what each of these letters stands for and how they relate to the amount of money or the interest rate that were given in the problem. The initial investment at the beginning of the account, if you will, was $1,000. That's the principal. So the way I'm going to use the 1,000 in the PERT formula is to replace P by 1,000. Also, at this time, the amount in the account is $1,750.67. That's the number for A. So we're going to replace A by $1,750.67. And lastly, the interest rate was given to us as 8%. But I don't want to leave that as a percentage and in this problem. I need to convert it to a decimal number before I can actually use it in the formula. Now, how do you convert 8% into a decimal number? Well, the answer is 0.08. Remember, to convert from a percent to a decimal, you shift the decimal point by 2 units in the left, or in the left direction, if you will. So you go from 8 to 0.8 to 0.08 or 0.08. So an R value or a rate of 8% is the same as 0.08. And that's very, very important. Now, if you plug that information in, the information for P and A and R, into the PERT formula, you'll have 1,750.67 equals 1,000 times E raised to the 0.08 times T. And notice now the only unknown in the problem is T. And that's exactly what you want to find. T is the time, and we've been asked to find how long the money has been in the account. So all I need to do now is isolate the T in that equation. And when I do so, I'll have the following. 1,750.67 equals 1,000 times e to the 0.08t. Dividing both sides by 1,000 is going to give me 1.75067 equals e to the 0.08t. Now, how do I get rid of that e on the right-hand side so I can get at that t, because t is what I really want? Well, I'm going to apply the natural logarithm function to both sides. And when I take the natural logarithm of both sides, I'll have ln of 1.75067 equals ln of e to the 0.08t. And the ln and the e counteract one another, if you will. They are inverses of one another. And so the equation actually becomes ln of 1.75067 equals 0.08t. And now you almost have t completely by itself. If you just divide both sides by 0.08, you'll have t equals ln of 1.75067 divided by 0.08. Now, I have no clue what that value of t is. That's a really messy looking number, but my calculator has an ln key on it, and most calculators do, which means I can actually use it to approximate this value of t. And when I do so, I'm going to find that ln of 1.75067 divided by 0.08 is approximately 6.99998. And how do I interpret that now? Well, that t value is a number of years that the money has been in the account. And so basically, the money has been in the account for 7 years. Now, by the way, I should note that this problem assumes that none of the money that was in the account has ever been taken out, or that any other extra money had been added in by the account holder other than that initial $1,000. So the only action to the account has been the bank depositing this interest on a continuous basis. The problem gets much more complicated if there were ever any withdrawals or extra deposits made into the account. Well, we've talked today about exponential functions and logarithmic functions and some of the ways that they can actually arise when you're trying to do sort of real-world problems. I can guarantee that there are other ways in which the natural logarithmic function and the exponential function e to the x show up in real-world problems. If you're interested in these kinds of functions, though, as I've mentioned in a previous lesson, you definitely want to look into taking a good pre-calculus or calculus course, because those courses will have you use these kinds of functions on a regular basis. Now, next time, we're going to move into our final section of the course, if you will. It's a set of 3 lessons on permutations, combinations, and probability. I'm sure that those don't sound like they're related to algebra in any way, but I promise you, I'm going to try very hard to convince you that they really are. I'll see you then.